want to thank Herman for joining us today. I first talked to building what we were calling X Sharp, which is no longer X Sharp, Xlang compiler, and it looked like a really interesting way to construct a compiler and avoid a lot of the kind of boilerplate work that goes on in such an effort like that. And anyway, I'm working with some folks here in MSR now on a new model checker, and so once again, I was thinking about how to go about building a compiler for this thing, and came back to Herman's stuff again, and I'm actually just starting to play with the code now, and so I was really interested in learning more about how the pieces fit together, just kind of getting my head wrapped around things. And I know there were a number of other folks in MSR that Herman had been talking to over the last several months or more. So it seemed like a really good time to bring Herman in and tell us more about CCI and maybe get the ball rolling on several projects, hopefully taking advantage of it. So thanks for joining us and doing this on such short notice.
Yeah, excellent. Right, yeah. Well, I was putting off doing a talk on this thing for quite a long time because I was hoping some kind PM will come along and do a really good talk. So this is going to be a dev talk. It's going to be mainly looking at code samples. I'm a little bit intimidated by the size of this. I expected about 3 or 4 people and dive into the code, that kind of thing. But okay, so as the title suggests, you can think of this CCI as being just another compiler. So, yeah, what's new? That was Yak is 27 years old now, and just so, well, what's the big deal? Okay. So, compilers aren't exactly new. I've gone back. Okay. So it's among other things a compiler. It's actually a little bit more than that. But if you think about what we're trying to end up with, so the reason why I'm working this at the moment is I'm involved in trying to make this happen, and I'm working on the writing that. And I really would like to have something that I can just go ka-chung and out pops the compiler. And although compilers have been around forever, it just so happens to be that there just isn't one of those things for .NET. There isn't one of those things that targets this Visual Studio part of it. And by the time you look at something like X Sharp, which is a superset of C Sharp, even though C Sharp on the face of it is quite a simple language, it seems so small and simple. It's actually quite a big language. And by the time you embed something in Visual Studio, it becomes quite a big job. So this is not a semester project for an undergrad. And there just isn't such a thing. So instead of just building this thing in some ad hoc fashion or just purpose-built, I'm trying to build this thing and plug in the spec and end up with that thing and then make this thing available for everyone. Now, it turns out that a better way of looking at the CCI perhaps is not so much as a generator, but as a framework or a collection of frameworks. So if you think of VS as being the VS IDE as being the overall framework or thing that we plug into, when you make a new language to fit into the Visual Studio environment, you are basically writing a number of packages which plug into Visual Studio. And so what the CCI is, it's a number of little pieces, or labeled CCI here, that you extend. So these are base classes that you derive from and you extend with your particular functionality. And you end up with all of these packages that then plug into VS. So we're talking not so much about some monolithic big machine with a crank that you plug in and something pops out, as a series of components that you can derive from and extend and build your things from. And these components become very interesting in their own right for other purposes. So you need not just build compilers with this thing. You can build all sorts of post-compilation tools or other language-related tools with these components. Okay, so just to give you some idea of who the appropriate contacts are, or the people working with these things, the project part of this framework is being the dev contact there is Frank Mantek. The debugger part is done by Samar Abbas. The language service is done by Wolfgang Manusek. I'm working on the code generator, the compiler part of that, along with Matt Warren, who's working principally on the query part of that. And there's also a central part here which represents something I call intermediate representation, which is used as a means of communication between all these different components. And I'm basically the person to contact about that. In the past, there's also been contributions by some of the people here in the room, Vikram, Rockyu, and a number of other people in MSR. So this already represents quite a substantial investment. A lot of people have already spent a fair amount of time on this. And the people on the screen are going to be working mostly on these components for much of the rest of the year. So it is already a substantial investment. So basically, another way of looking at this is saying is that the resulting components, or the library of components that come out of this, should be seen really as the library for building a managed compiler on .NET. The V is emphasized there. So this is basically saying, so there's a lot of work. If you're thinking of rolling your own, well, just don't even think about it. It's still in an early stage of development. There's been a lot of prototyping. There still has to be a lot of work has to go in there. But it's already attracted a lot of investment in the past, and it's having a lot of investment right now. And it's being used for more and more things within the company. So there's hopefully, maybe I'm over-optimistic, but hopefully there's some sort of bandwagon effect taking place here now. But it's still early enough that if you have particular uses for this, that you could probably have some real influence on the design, and you can maybe help clean up and make this thing suit your needs better if you have something like that. So for many of the uses that you could use this thing for, apart maybe from the Visual Studio embedding, but post-compilation tools and just general working with code on .NET, you could use the system reflection. You could use the system reflection emit to build a compiler even, and you can use the system codom libraries for much of the things that you can do here. But you need not. You can use the CCI to do all of these things as well. I've used all of those things, particularly in building a JavaScript compiler, and my heartfelt advice to you is just say no. Those libraries are not ideal for doing compiler kind of stuff. Hopefully the CCI is a better deal than this, and if it's not good enough, then you can probably help make it better. Yes?
So I'm a little bit confused. The CCI is useful for Visual Studio, which is a big infrastructure. It's also useful for building things that fit into small applications that you're able to do.
Yes. That's the benefit of this being just really a library of components. So these components stand by themselves, and while they are useful for doing a Visual Studio embedding, you can also use them outside of Visual Studio. So you can build command line compilers or post-compilation tools, and there's been work like that done in MSR already. So Mike Barnett and Rob Deline and Manuel Funder has done stuff like that. The FXCOP tool is looking to adopt the CCI to do the next version of the FXCOP. Okay, so currently these the libraries package as two DLL, system compiler.dll and system compiler framework DLL. It may well just be combined into a single DLL in the future. But the first DLL essentially just defines the IR and a means of reading in assemblies and writing out assemblies. And pretty much amounts to the replacement for system reflection and system reflection emit.
Question.
Sure.
We are talking about replace system reflection. Does that also mean that you can execute code which you manage by the CLI?
Yes, you can, after you've generated an assembly, you can load it in to the system using system assembly.load or something. And after that, you can reflect on it using reflection and execute that. Probably there's some scope for adding more helper routines in the CCI as it is to do some of that stuff under the covers for it. And as the new reflection capabilities and dynamic reflection comes out in Whitby, that probably will be a future direction.
What's the future direction for you to start using reflection, or are you going to? You said as the new reflection comes out in Whitby, that's.
So what's coming out in Whitby is the capability of injecting code dynamically into assemblies without emitting a whole new assembly every time. And so it would be it would be nice to have some sort of help for that. A quick and easy way of leveraging the code generation capabilities of the CCI to generate code like that. But this is still in the future. Right now you have to basically build a complete assembly or a module and then load that. So the only way to do dynamic code execution is by loading assemblies, which is pretty much the VS7 story.
Is there a quick version of what the issues that you found with the system reflection, or?
Yeah. So one of the problems of system of reflection is that it provides you with a read-only object model. So you can't build one of these things yourself. So this is purely an import mechanism, not something that you can use as your own AST, for example. And it's not something that you can build in an export. The system reflection emit is a parallel hierarchy, which is a write-only model, and it has to be constructed in a particular way. The other part is that because system reflection exposes most of its functionality as arrays, a lot of the collections come back as arrays, but it's read-only. Every time you ask for a collection, you get a new array, which makes a copy. And a lot of the indexing into the model is done using strings, which are particularly a bad way of doing lookups in .NET, because, strings don't hash very well. And sometimes you just do linear searches. So there's a large amount of performance problems with reflection. Also, reflection is not a complete model. It doesn't expose everything in metadata. So there's some things you can't do with it. Okay, the object model of intermediate representation looks actually quite a lot like reflection. You can think of it as being the object model that you get when you throw reflection into a pot, you throw reflection emit into a pot, you throw the codom into a pot, you mix it all up, and you clean it up a little bit, and you pull it all out. At the root of it all, there's a base class node, and then there's a series of fairly fundamental base classes that everything hangs off. And if you are reading in an assembly, then you typically will get back a module, and an assembly is seen as a subclass of module that just has a manifest. And if you're looking at it as a codom kind of thing, as a AST, then the root node typically is compilation unit. And then there's a root node for types, and a type's a collection of members, and a type itself can be a member, and so on. And then what it adds to reflection itself is the concept of statements and expressions, which pretty much model AST-like concepts over method bodies. So you can model a method body as a normal AST-like construct, which is a little bit different from the reflection emit model, where a method body typically is just a stream of bytes, a stream of instructions, a linearized stream of instructions. Right, so essentially it's metadata, it's IL, it's traditional AST, it's all modeled with a single object model. So some of the things to note is that every node carries with it a field which is an enumerated scalar indicating what type of node it is. So that if you are dealing with a tree which is some base class and you want to do something depending on the actual concrete instance, that you don't have to go and do type tests. You can actually switch on this type tag. So it allows for efficient switching, which is something that the codom is missing. Another thing that every node has is that it has an integer key which is unique to that node so that you can hash it efficiently. So you can insert the node into a hash table using only an integer, and when you have when you find it in a hash table, you can establish that you've got the right node by just looking at this, just doing an integer comparison. Some node types, such as binary expression, which tend to be leaf nodes, are further specialized by means of this node type key. So instead of having a special node for plus and another one for sub and so on, it's just all binary expression, and we use the node type field to further distinguish, when the only thing that's different between the various children would just be the fact that they have a different identity. Okay, another thing that the object model does is it abstracts away a little bit from IL in the sense that there are no encoding issues, that you don't have all the various different ways of loading a constant. You just have a node for constant. And when you write out one of these trees, the writing process decides automatically which encoding is the most efficient one to use. Okay, so there is this object model that covers all of IL and metadata and pretty much all of the codom. And you can look at an existing assembly and you can read it in by just using assembly. Actually, it's not assembly, it's assembly node, sorry. Assembly.getAssembly with some path or something, and then you get back this root node, and it is this tree, which is a lazy tree. It's constructed as you need it. Or you can get a module if you're not reading an assembly. And likewise, given a module or an assembly, you can write it out to a stream of bytes using write module. So in this sense, it's pretty much like reflection or reflection emit. You can read memory streams and write memory streams with it, so you're not bound to go to files, unlike reflection emit. You can also create PDB files, and you can create those in memory as well. When you write out one of these trees to an assembly, the tree cannot just be any tree. It has to be in what's called a normal form. So basically, there is some subset of IR which corresponds in a more or less one-to-one fashion with IL. And as long as your tree is in that format, you can write it out and persist that. So in this sense, it is just a replacement for reflection emit. And a typical reaction that I see is that people say, oh, well, I've got my language, and I want to write a compiler, and system reflection is a bit slow, system reflection emit's a bit slow, so I'll use this thing. But what I'll do is I'll make my own AST, I'll translate it down into this normalized tree, and now I'm done. And you can do that, but it's not really what I recommend. In order to make use of the whole component nature of the system and the integration into VS, you really want to use the nodes that are there and possibly extend them with nodes that are missing. So if you're looking at your language, you've got some concepts which have no direct analog in the standard IR. So what you need to do is just create classes which extend appropriate base classes in the existing object model. You make up your own node type enumeration, which you just have to make sure that that's distinct from the standard one, possibly distinct from any other ones. And then note that in the basic IR, all fields are public and all methods are virtual, so you can customize what happens there. But for the most part, IR is just passive data. There's not much there in the line of methods. Most of the methods have to do with some sort of reflection capability, being able to read in metadata and reflect over it and find stuff, simple table capability. But basically everything is available and changeable. Right, now, since the data model that you get, that you use to represent your AST or that you use to read in metadata is largely passive. It's just really the data. All the behavior, all the compilation behavior that you need is factored out into separate classes, which I call visitors. So this is not really the standard visitor pattern as such. It's just, I just call them visitors. But so there's a base class visitor, which is really just defines a single method, which is visit this node type, which is used for some derived classes. But most visitors extend this thing called standard visitor. And standard visitor is, overrides this single generic dispatch method visit, which basically just switches on the node type, and depending on the node type, it calls a particular visitor method for that particular node type. So it casts the node down to the actual type it is, and it calls this particular one, and there's an example of a particular visitor. And by extending the standard visitor, what you do is you just override the methods for the particular node types that this visitor is interested in. So you can start, and what the standard visitor basically does, it just walks down a hierarchy in a natural order. So it basically pretty much ensures that every node is visited. And then your extended visitor just overrides particular methods. And so it's basically almost a pattern match thing. Like you can say that when I get to this node, I want to do something. And when I get to that one, I want to do something. And you don't have to do any of the traversal yourself. So all of the traversal is already there, and you just define what you really want. Okay, so some of the concerns that people have with this is that there's this sort of double dispatch. Yeah.
So if I want to override what the visitor does for one entire subtree, I can just go to the root of the subtree and just override it at that level. And then things will automatically happen for everything in the class hierarchy that's below that subtree.
Yeah, actually, no, it's not quite that simple. Basically, visit knows about all subtypes, and that would be the one that you override. Or you would override it for a particular method. The other subclasses do not really play much of a role. There is something like a visit expression which you could override, but what it basically does is it just calls visit and then casts the result back to an expression.
Herman?
Yes?
So what kind of operations would actually require visiting all the nodes? Like, for example, serializing. If you want to serialize, I'm assuming that if you want to serialize a module or an assembly as code, then that would invoke that visitor, the top-level visitor, which would call visitor on every node. Would call visit on every node.
Well, a serializer perhaps is not the best example because you very likely want to override every single method in that one. But some other visitors, you maybe want to do only something for identifiers. So you can override the visit identifier method, and you don't have to do any of the others.
So there's one well-known problem with visitors. It's called, some call it 90-degree problem. So if you add a new node type, then you have to go to the visitor class, change the visitor class.
So
if you set,
I've got some slides to address that question. Okay. So one of the things that you may notice that, well, so people have pointed out, is that there's really a double dispatch going on here. First we go to visit, which does this switch on essentially some sort of vtable, if you like. And then we do a virtual call to this thing. Now we do a virtual call in order to enable you to override a visitor. But now you're basically doing a double dispatch. And people say, oh, that's inefficient. Well, yes, but this is the only way that you componentize the thing. Is that you could stick with virtual methods if you put the methods directly in the node classes. But then the node type has to know about all possible visitors. Or you could make these calls non-virtual, but then you can't override them and specialize visitors. So basically, in the interest of making things flexible and using these things as components and minimizing code, it's just, well, we'll just put up with a double dispatch. It turns out that the performance impact of that is not significant. It doesn't show up as being a problem. Because when you're compiling there, you do a lot of work elsewhere, and the dispatch of the tree walk is not the critical bottleneck. Okay, so the other problem that comes up is now, well, this switch here just knows about the built-in standard node types. Now, you've gone to find your own node types, but this standard visitor, this is a separately compiled component that knows nothing about your node types. Now what? Okay, well, the very last thing on that switch is a call to visit unknown node type, which is a virtual method which can be overridden, of course. And so visit unknown node type, its default behavior is to actually go and call yet another thing, which is said, get me the right visitor for this thing, and then invokes that visitor, and get visitor for, of course, is virtual in itself. Now, this built-in scheme is what you use to provide behavior for your additional node types. So now, if you've gone and defined some new node types and you now want to make your own new standard visitor, you basically override or you extend standard visitor, and then you can do a couple of things. One of the things you can do is you can override visit. So you will go in here, you will look at the node, you will unsafely, if you like, cast that enum to your own enum, and then provided that your range is separate from the built-in range, you can then take care of all of the node types that you know about, that's your node types. And then when you get to the default, which is the standard node types, you can just call back to the base class method, which will then invoke the visitors for that. Now here we've done the double dispatch into a triple dispatch. So that's just one of those things. Another way of doing this is that you could actually just override visit unknown node type, and it's the same thing. So, so this will be invoked only if the node type is not known. So first you will go to the visit. Whenever you call visit, you go to the standard visitor visit, and only if it gets to a case it doesn't know about will it get to this one, and then have an opportunity of doing your particular node types. So you can do either one of the two. The trade-off essentially is if you expect that most calls will be to the standard node types and your own node types are very few, then this is probably the best way to do it, because in most cases you're doing a double dispatch instead of a triple dispatch. If most of the node types are your own, then doing it the other way is probably better. But this is how we are able to add additional node types, or additional nodes to this thing, and have these separate visitors. So this allows us to do two things. We can add visitors to the standard scheme. So we can add non-standard visitors, visitors that have not been anticipated, and we can make visitors deal with node types that have not been anticipated. And by having this double dispatch, it's how we make the thing extensible in two ways. So either rather than just putting all the visitors in the node types, which makes that extensible, or making the visitors extensible but the node types not. Okay. So in system.compiler, there's a collection of some basic visitors. Sort of a trivial one, visitor, which is just almost useful as some sort of delegate. It just, if you know nothing further about the visitor, well, it just defines the virtual method visit. So you know if you have one of these things, you can at least call visit. If you know nothing else. Standard visitor derives from visitor, and that is guaranteed to traverse all of the standard nodes by doing a depth-first traversal. So you may not always want to do a complete walk of the tree, which is why there is the other possibility of visit, which doesn't do that complete walk. Then there's a thing called standard checking visitor, which provides a whole bunch of helper routines that call into a component for reporting errors. So if you are going to walk through a tree in order to do some error checking or error reporting, then standard checking visitor probably is the one to use. There's another one, duplicator, which does makes a self-consistent copy of any particular tree. So it fixes up any references. So if you have a module and you want to make a copy of that module, then any references to types of that module, so any self-references, will be duplicated so that the references in a copy of the module is to the copy, not to the original one. There is a visitor unstacker, which basically removes all push, pop, and dupe instructions from the IL. Those instructions are problematic because they are, in IL, they're essentially untyped. And you need to do a bit of flow analysis to figure out what the types are. So this visitor does the necessary analysis and actually then just gets rid of those instructions and replaces them with locals. And then there's a thing called specializer, which essentially is an extension of duplicator, and it can take a tree and duplicate it while replacing certain things. Basically, anything that shows up as being a type parameter. There's a special type parameter, class parameter, interface parameter nodes. And so you can use this to provide some sort of template instantiation ability. And these are fairly basic and just operate on trees per se. And okay, now I'm going to be talking now about the compilation framework for a bit. So I'm done with the IR part of that. So the compilation framework is what you use to build compilers. So if you want to build a command line compiler or maybe a compiler that is invocable from a Visual Studio project system, you basically start with this abstract class compiler, which is the framework for compilers, and you extend that. Now, this class implements the system codom.i code compiler thingy. So you can use this class anywhere as a codom provider. It provides a whole bunch of methods that deal with compiling this, that, and the other thing. It has helpers for parsing command line options, and it has a whole bunch of plumbing. So it's a fairly big class with a lot of complexity in it. Using this class, you can build a command line compiler very easily. Essentially, command line compiler becomes almost just a trivial little wrapper over this class. And this is also the standard class that other parts of the framework use. When they need a compiler, they need to talk to a compiler, they talk via this class, so they don't have to have specific knowledge of a compiler. It's just, well, your compiler, but I'll use these methods to talk to it. All of these methods, in the end, boil down to calling this abstract method compile. So this basically reduces whatever comes into it into a tree, an IR tree, which hangs off compilation unit. It provides it with a global scope, which is if this tree has to be compiled in some predefined namespace, or if there is wherever you put your globals, if you have globals. And it provides it with a list where you can add any errors that you find as you provide it. As you compile this, and if you find errors, you add error nodes to this list. And when that comes back, then the compiler takes care of doing something with the errors and reporting back and so on. The compilation unit has a field which contains the target module, so you know which assembly or module that you want to that you must emit types into. Now, you're free to implement this method any old way that you want. So you could, if you wanted to, you could do the codom trick, which is just take that tree, walk it, turn it into a source, spin up a process, call the command line compiler, and hand back the assembly that was load in the file, hand back the assembly. You could do that. But, of course, that's not the recommended way. So this is the recommended way. Or at least some variation of this is what you should do. So in your class that extends system compiler, you should override this method and make use of a bunch of standard visitors, or rather your overrides of standard visitors, to transform this compilation unit into an assembly. So the first thing to look at there is this base class error handler, which provides us a whole bunch of utility routines for, here's a type, give me some nice string to display the type, or here's a field, give me some nice string that identifies this field, or here's a method, give me a nice method signature. Just all these things that you put into error messages, and takes care of localization. Well, that's all part of error and so on, but it allows you a way to customize the way that error messages are displayed. So you make one of those components. So typically, an error handler would be your override of the system error handler. And because this is in your derivation of compiler, you get to specify which class that is. So as far as the system is concerned, it's going to deal with the base class error handler, but you get to you instantiate the one that you've overridden. It's your specific one. Okay, so the compilation proceeds essentially in 4 phases, or typical compilation. The first one, just a symbol table lookup, essentially. So it goes through a tree, and it just, whenever it sees an identifier, it actually uses the scope chain to bind this to a particular thing. It also looks at signatures. So if you visit a method and the type of the method is some expression, or itself has to be looked up. So by the time you've gone through Looker, all of your signatures are resolved. So all of the methods, the return types are known, the parameter types are known, all of the fields, the field types are known, and so on. So after you've run through Looker, you basically have to not worry about the scope chain anymore. So after this, the scope chain is irrelevant. The next phase is resolver, which essentially does type resolution and overload resolution. So it goes through now, if you have a method call, it will work up the tree, figure out what the types of the parameters are, choose the appropriate overload. So following this, all method calls are resolved to particular overloads, and all expressions, the tree now is well typed. You can ask any expression or sub-expression, what is the type of your result? Yes?
Was there a reason that you didn't do that in the original Looker pass?
Yes. Because when you're doing type resolution, you need to know what the types, if you're calling a method, you need to know what the result type of the method is. Now, if the method is one of your own methods, and that type hasn't yet been resolved, then you have to first go and figure out that type. So
is it just an ordering?
Yes. So it's partly an ordering thing, and partly it turns out that this componentization is quite useful for other uses.
That would be a function of your depth first search, I guess, having the ordering problems.
Yeah, so this avoids some ordering problems, and it also provides a useful way of avoiding work later on. So one of the concerns that comes up with this is that, wow, 4 passes, and we all know that multi-pass compilers are bad. And you're doing 4 passes here, wow, and this is just not on. Well, yes, not only are we doing 4 passes, but we all have all those multiple dispatch things. So it seems bad, but it turns out that most of the work you do in the compiler is you do in other places. It's symbol table lookup, it's this thing, it's that thing. It's, what we're doing is we're taking a small constant and multiplying it by 10 or something, and the result is still a small constant that you apply to. So you're not going from linear to nonlinear. You're just making your constant a bit bigger, and it turns out not to be a particularly noticeable impact. So you're going to be slower than a purpose-written compiler. You're going to be much slower, well, say 4 or 5 times slower than a C# compiler. But it turns out that that's not.
Is it an actual number for 5 times slower than the C# compiler?
Well, if we're comparing apples to apples, running through the C# test suite with the X# compiler, using their automation system, it takes about 4 times longer. If we cheat and we use the in-memory compilation feature, then we go from 4 hours to 16 minutes. So we can compile and run the entire C# test suite in 16 minutes.
7,000 tests.
Yeah. And this is just because we don't have to start up the runtime for every test case. So probably the most time that we spend in a typical compilation scenario is just starting up the runtime. The actual compilation is negligible. Importing metadata is the other big thing. So they're running through these trees, even though this looks very bad, it's not that bad. So you do most of your work somewhere else, so the tree traversal time is something that, although it looks bad, you can just put out of your mind. And it's part of the price you pay for componentization and flexibility. And it turns out this is well worth paying. It's not an issue. Okay, so resolver, by the time you've done resolver, you know what methods you are calling, even though perhaps virtual, you know the types of all expressions. The next thing, checker, is essentially just all remaining error checks. Are the methods that you're calling, are they actually visible? If you're deriving from a class, are you implementing all abstract methods and blah, blah, blah. This is the most complex phase, actually. There's a whole bunch of error checks that you do here. But by the time you do these checks, at least you know all the types and so on. Once checker is done, we call normalizer, which takes the tree from its AST-like format and turns it into normalized IR, which essentially is the code generator. And you may have noticed in some of the previous visitors that there's a lot of null checks. So if the thing that you're calling this thing on is null, then just return nothing or do something or do nothing. The basic error recovery strategy is that if you find an error in some node, you recover from it by just replacing it with null. So as the tree gets transformed, if there are errors in it, you just gradually prune it away by putting null in there. So as long as you, in the visitors, which standard visitor does already, you check for null and just ignore it, there's quite good error recovery in the scheme. Okay, so that's the basic scheme. I think I've talked about, I've talked about these things now. Right, so that's compilation. That's pretty much all I'm going to say about compilation. If I have time towards the end, there are some interesting wrinkles that you can do about that, such as compiling different languages together in one tree, such as having embedded languages. And we've got some interesting things we can do with things we call compiler plugins. What I want to talk about now is how we do the embedding into Visual Studio, because it's a fairly involved scenario, and it also shows how the componentization pays off. So writing a command line compiler is a relatively simple job, right? You just take in a text file, you produce an assembly, and you're done. Sitting in Visual Studio is another matter altogether. Now you want to have the squigglies come up as you type. You want to have statement completion, tool tips, and a whole bunch of stuff, right? And so for the C# compiler, right, there's two separate teams almost. There's the one team that does the command line compiler and another one who does the Visual Studio embedding. And it's a big enough job that you won't have separate people doing that. And so this adds to the cost of making a compiler and putting it into Visual Studio. So I just want to walk through how we do a language service. Now, so there's a base class, language service, which provides the package in Visual Studio which provides the language service. And what you will do is you will extend this. And it turns out that your extension typically does nothing. The current implementation of language service utilizes a component Babel that was created by an intern, which is a very nice abstraction over the VSIP interfaces, but it's limited to functionality. It's just to get going. So this will be replaced at some point, and we will go directly to the VSIP interfaces.
Originally, I thought that Babel required you to write a Alexa YAC file customizing language.
No, that's just an option in Babel. Babel has this interface iBabel service, which you can implement yourself. So they have a standard implementation that implements this interface, which uses LAC and EX, or you can implement iBabel service yourself. And so we use that facility in Babel, which got us going very quickly. But in the end, it's limited and somewhat awkward, and we'll write our own thing. But the experience in using language service is not expected to change very much. So essentially what happens when you use Babel service is that the VS environment calls into this language service in two ways. One is, here's a line, just one line of text, color it for me. And there's a little bit of state there. And Vikram is the guy who did most of this work. So I'm just basically, hopefully not misrepresenting his work too much, but Vikram is the man. All right, so the color line is called from the foreground thread. And then there's a second method, parse source, which sometimes is called from the foreground and sometimes from the background. But essentially, you're given the current window as a string of text, a place where you can call back, and some reason why were you called. So essentially what happens is the color line, when you call color line, you call back to the Visual Studio environment and telling it, this particular token has this meaning. So if you are scanning an open parentheses, then you go call back to Visual Studio saying, well, this is an open parenthesis, so this is an interesting thing. So when Visual Studio finds out that the current cursor position or current type character is an interesting character, or the mouse is hovering over an interesting thing, then it calls back to parse source and say, oh, I found an interesting event and I want you to tell me something about this. What Visual Studio also does is on its background thread, it calls parse source with the complete file from time to time and says, just run through this thing and find me all the errors in there. Sure.
I thought the rumor that Babel will not make it in NET 2003. If that happens, and if you're going to, as you said, later you will exchange basement on Babel, do you keep that interface? Is that the plan, or do you also plan?
Yes, so that interface will probably change. So this really is the interface that VS uses, or Babel uses to talk to us. It's not. It's helping me to explain this rather convoluted way in which a language service works, but it's not an interface that you would expect to use yourself. Unless you were writing your own, at this moment, if you were writing your own shell, for example, if you were trying to replace VS, and you were wanting to use a CCI compiler and embed that, then you would call this interface. You would not otherwise worry about it. That answer? Okay. So, just drilling down a little bit of what happens with color line is that when the language service is initialized, and the way this happens is that you go and you write a derived class. You go and write your own derivation of language service, and then you register this derived class in the VS registry as being the thing to invoke when you see this particular extension. So when VS starts editing your file, it instantiates an instance of your class. And so when this instance is created, one of the things that your derivation is supposed to do is to fill in that field, scanner, with an instance of your scanner, which is expected to be componentized by extending this scanner base class. So it knows how to talk to, so this generic plumbing code knows how to talk to scanners in general, and as long as your scanner implements this interface of the base class, you need not do anything further because the plumbing code will just work for you then. So the contract with scanner is simply that you should be able to take a scanner and say, okay, here's a particular line of text, and I want you to scan this. And then after initializing the scanner, you want to just call it and say, okay, scan me a token, and fill in this token info object with just a little bit of information about the token. And you pass in the state, and the scanner must update the state so that the state passes from one token to the next across lines. So this is how you figure out whether you're inside a comment or not, and so on. And so you just basically run through this line, scanning the tokens one by one, and then you call back to VS, which is the sink there. And so every time you get a token, you call back and say, okay, well, I found a token, it starts at this column, it ends at that column, it should have this color and this kind of thing. And this is what VS then uses to find out whether it's at an interesting location or not, and to do syntax coloring. Okay. So parse source so it's called in two modes. The one is from the background thread. It's just, here's the whole file, just compile it and report errors. And so it comes in with a reason, and the reason for that is just to check. And essentially what happens is that we set up some callback information, then call this helper routine to just do something with the text. We get back an error list, which we will then call back to VS in an appropriate way with these errors. So that's a bit of plumbing you don't have to write. And then the other thing we do is that we use the compiled version of this file to package up some state about the program, so that when we get to interesting events later on, that we have some semantic information that we can use to do something with these interesting events. So it sends back to VS an authoring scope, or rather to Babel an authoring scope. Okay. Now this helper method essentially that relies again, in this case, on the parser base class. So there's a base class for all parsers. So as long as your parser component extends this base class, the plumbing code will just work for you. And again, it's expected to have been initialized there when you started up the language service. So your derivation of the language service finds the right parser from somewhere, sticks it in there, and after that, the plumbing code just talks to this thing using its standard, this is what a parser should look like. And it does a couple of things. First, it figures out, based on the caller, what is the current project. It finds out, well, I'm inside VS, there's a project open, right? And it needs to get the project because that's where all the files are, and all the project settings and the compiler settings, all the things that you need to actually do a proper compilation of the thing. Then it calls the parser. It gets project options from the project, calls the parser and says, okay, here's a string. Oops. Here's a string. Give me back a compilation unit. And it holds on to this. So back comes an IR tree. So the componentization of the parser is a way of getting from a string to this IR tree. Now the next thing that happens is that we go to the project and we find out all the other files. So what happens is that every file in the project is compiled separately to a separate little module. And this is only for the purposes of the language service. So when we find the project for the first time, we go and we take every file in the project, parse it, and then, well, we take one by one. We take a file, parse it, and then just run the looker phase over it. So all it does is it just resolves the type signatures of all the things. And it even, well, not right now, but in principle, it will ignore the body. So it will just parse the file and then run through it quickly and resolve all the signatures. So it just have the signatures available. And it then packages this thing up into a module so that it can be treated as a separately compiled unit. So it basically scans all the files in the project for signatures and keeps this around in the project object. And so what it does with this file that you come in that you want to do a full check on is that you make a new module for this file and you put in all the other files in the same project as separate modules, separately compiled modules. And you make module references to them. So this is how you can discover signatures from your own project without actually having compiled them in the first place. So this is one of the cases where it's nice to have the looker as a separate component because you don't need to analyze any bodies. And for analyzing the signatures, looker is sufficient and the cheapest way to do that. So once we've set up the references to the other files, which is not the file that we're compiling now, we call a helper method to parse and analyze and fully compile this particular source, well, we've already parsed the compilation unit. Now we're going to take this parse compilation unit and we're going to run essentially looker, resolver, and checker on it using the well, the project's already been set up in part of compilation unit, and we give it an error list, and then we remember the result of this compilation for next time, so that if that file has changed, then we don't need to compile it again. So we keep on updating this project. Every time we visit a file and we call this thing, we update it so that it stays current. Otherwise, it would just be whatever it was when you opened up the project for the first time. And then we're done. So this is the background compilation step for a particular file. So from time to time in the background thread, we take this file, we compile it in the context of all the other files in the project, but we do the full compilation only on that file. And we do a partial compilation on all the other files in the project. So just to make it scale a little bit better, here's the implementation of analyze parse tree. So essentially it's the same as the compiler, except that in this case we don't bother to go to code. So there's no normalization step. So it's using the looker, resolver, and checker. So the nice thing about this is that unlike the current C# Visual Studio implementation, where you get only syntax errors, and you actually have to hit build before you get any semantic errors, because we're running essentially a full compilation, but only on this file. We get full error reporting. Everything comes up as you type. Because it happens in the background thread, there's no build, whatever, so you get constant, complete error feedback on this. And it seems to be fast enough because, on the whole, you apply it only to one file, so it doesn't become impossible if you have a really large project. Okay. Now, that's the background thread. Now, in the foreground thread, we said that we're going to call color line, and every now and then we get to an interesting character. And then Babel or VS wants to find out more about this interesting character. And it says, okay, well, I found an interesting character, and I'm calling you because I want to do the following action. I want to give a method tip, or I want to do a statement completion, or I want to give parameter information. So there's all of these reasons that come in. And then the other thing that I'm not sure whether this is Visual Studio that does this or whether it's just Babel, but you get a string that runs from the beginning of the file until just a little bit beyond the interesting character. So you get a partial string that represents the current source position. It starts from the beginning so that you can parse it, but it doesn't bother to parse you the rest of the file. Well, we take that string and we compile it into a partial parse tree, partial compilation unit, and we store that away for future reference. And the other thing that happens is that as you compile this tree, you call back to VS and saying, well, I've parsed the string now, and now semantically I found that I'm at the following thing. I'm at an identifier, or I'm at a method call or something like that. So you call back saying, I'm at the position that's interesting. So the other thing that comes in is that we are given well, I forget where some somewhere in there there's the interesting position, or the position that you found that you want to know about. And as you find that interesting position, you call back. Basically, so you call back to VS and say, okay, I found this stuff. Then what Babel does, and this is where it gets kind of convoluted, is that it says, oh, well, okay, so at this position I found this following thing. Now I'll go back to the previous background compilation thread. And from that, the result was some symbol table. And I'll then go to the symbol table and say, well, what can you tell me about this position? So to put this in a more graphical format, okay, so what happens is that in the foreground, we get this partial piece of text. we compile it to, VS then reads this in and it provides it to the language service. The language service passes that to the parser. The parser creates one of those trees, and it also calls back to Babel or the authoring thing saying, these are the interesting semantic or these are interesting syntactic positions in the text that are found. And then, meanwhile, in the background, we've taken the entire file, we've compiled it to a complete tree, and we've wrapped it up with an authoring scope. And then, once we've called back and we've returned control to VS, it then calls back into the language service, and now the language service does with the position, saying at this position, I want to figure out what this thing. So basically, in the first one, if you find an identifier and call back to VS saying, I find an identifier, then VS, if you had a cursor over that, for example, say, okay, now I want a tooltip. Or if you were at an open brace or something like that, it will do. But so you call back. It then runs through this tree, which is the whole fragment, so there's a special visitor method finder that just goes and finds the method body that contains the interesting cursor position. And then a second visitor is called on the original tree that we got from the full compile. And we then graft in this method body of the partial text, which is the most recent version of the text that we have, into the overall compilation tree that we got from the full compile. So now we have a combination of two files, really. But we're only interested in the method body of the current text. What then happens is that we run looker only on the method body, but within the context that we have already established with the previous compilation. So one of the things that the method did is it held on to its scope. So we still have the scope chain available. And so we just rerun looker on that scope. And so it reanalyzes the method body using all the information we've already gathered. Then it runs resolver, which now runs in the context of the complete thing. So it even sees forward references that you had available from the previous parse. And following that, well, there's no need to do checker here because we're not trying to give errors. We run a special visitor called authoring visitor, which now will run through the tree, find the place that corresponds to the interesting position. And now with the tree having been fully analyzed, that we know which method we are calling, we know the types of all expressions, we can now report back to VS with full type information. So it's even nicer now than with C#. If you get to a method, even though all the parameters are there, it gives you all of the overloads. Now, with this scheme, if you have available all of the parameters, you can give back the particular overload. So you don't have to say, well, it's one of the following overloads. You can do the particular one. Because you've done a full semantic analysis, you have everything available, all the type information. You can give rather accurate feedback to that. And so here's a scheme where we've used the componentization of having only looker and resolver. So some stage we use only looker. Here we use only looker and resolver. With the background checking, we use only looker, resolver, and checker. And with compilation, we use all four passes. So the componentization actually, apart from making it easier to do forward references, works out quite well in doing this rather convoluted scenario of the language service. Now, the thing is, all of this plumbing is done in the base class of language service. It's really not your concern. You have to write looker and resolver and checker, which you have to do for the baseline compiler anyways. You have to make authoring visitor and pruner and the other specific visitors aware of your new node types, if any, just to be able to traverse the tree past those nodes. But then you're done. You don't really have to do any more additional work to get full integration into VS. So a lot of this rather difficult stuff comes essentially for free because of the componentization of this thing. Okay. So much for the language service. Now, the other framework is the project framework. This is still in an early stage of development. What's checked in on the source tree at the moment was mostly done by Chris Lovett. Frank Mantek is working on it at the moment, and we're running into quite a few bugs in VS because none of this code has ever been exercised from managed code in VS. And so a lot of bugs that are latent in the VS7 source code have never been discovered, and are now being discovered because, unlike all the other project systems, this is going by interop, which exercises some code paths that have not been tested. So we have some dependencies on WIDB to make the project really work, but there is some rudimentary functionality that you can run on VS7. The project largely stands alone. It does all this UI in VS, and it will be done as a class hierarchy with lots of virtual methods and points of extension that you can customize and do your own thing. But if you satisfy just with a standard C# kind of project, then you don't really have to do very much. You have to supply a few strings about the name of your project and the name of your language and so on. But all a project really does is that it provides options to the compiler. So as long as the compiler knows how to obtain information from the project in a standard way, which the base class of compiler already does, you're covered. And as far as the project is concerned, all it wants to do is wants to call the compiler and say, okay, well, here's my, I want to compile this project and get an assembly back. And so it talks to your compiler using the base class compiler and doesn't really need to know anything specific about your language. How am I doing for time? 10:30, 12, almost now. Okay, so it's a huge chunk of code. It's largely in a world of its own, and unless you have very specific needs for a project, if you were just a language implementer, you wouldn't worry about this too much. If you want to just do a specific kind of project and not worry about a compiler, then you can use this framework pretty much on itself. And maybe just have some specialized compiler that does something else, if you're not interested in IntelliSense or so. The other framework is a debugger, where Vikram, again, is the person who started this off. Again, there's a big chunk of code here to interact with all the various APIs. There's a lot of APIs, there's a lot of plumbing and tricky and difficult stuff. But ultimately, what you want to specialize for a generic debugger to your own language is you want any expressions that you type in for breakpoints or in a watch window and so on must be expressions in your language, and you want types to display in the right way and so on. So essentially, this functionality is already componentized in compiler. So you can take any string, and compiler provides the ability to say, compile the string as an expression. So you can just use the existing compiler already. Much of the formatting issues are taken care of by the error handler component, which is used to do compilation anyways. And the only additional thing is that when you evaluate these expressions in the watch window and so on, you don't want to go and generate code, emit an assembly, and run that. You want to basically take this normalized IR tree that results from compiling this expression, and you want to interpret it. So there's a little interpreter for, essentially, not really for IL, but for normalized IR or IR in general. And it turns out that this interpreter is also quite useful for the compiler itself, because the compiler has to do constant folding. So the compiler has a need for compile time expression evaluation without first emitting code and loading and running that. So again, there's commonality. So you're just reusing components, and there's very little you have to do to get a customized language-specific debugger for your language. Now, if you have a very extended type system and lots of very specific semantics, as JavaScript, for example, you need to do a bit more work. But for a typical statically typed compiled language, the compiler pretty much, the debugger pretty much comes for free. And this, again, is typically, if you do it the old way, this is a chunk of work. For JavaScript, we had Vikram doing this for almost the whole dev cycle.
This interpreter runs in the context of the application domain, or how does it get values from the actual debug?
So when the interpreter, when the interpreter is used for constant evaluation, constant folding, it really doesn't need much constant. It's just working on constants. If it's used in a debugger context, it has to get scope information. Well, it has to have an environment that it runs in. Yeah.
So the current bindings of...
And the plumbing to do this uses the debugger APIs for inspecting the state of the debug process. So there's a lot of code to write there.
Debugger API.
But, yeah.
Because we actually interested in functionality for test case generation, for example. We have an application running in an application domain. With some expression, it's not debugging. In the context of that application, which is, I think, an interesting functionality.
So the debugger framework essentially uses the debugger APIs to inspect and manipulate the state of this separate process. And there's a lot of work. It's not trivial to do. But essentially all of this is taken care of in the plumbing. And as long as the evaluator, as long as you can take an expression, compile it, and then use that compiled expression and evaluate it using these components, essentially you don't have to do any special work for your language. You can just use the standard implementation. So there's a chunk of work here, but essentially you get it for free. Not much you have to do about it. Okay, we're almost out of time, but if you're not writing a compiler, and few of us have the luxury of writing new compilers and new languages, there's still a lot of other interesting things you can do with languages. A lot of people are using writing custom checkers. There's FXCOP. There's the XAF framework has got some specialized post-compilation tools for checking properties. There's an MSR. Rob and Manuel have been doing custom checkers. So your language, and this is the case for going to be the case for X#, can extend this basic compile routine and provide some hooks for running custom checkers. So one way would be to, after we've run checker, we can go to our compiler options or to our reference assemblies or something and go find out whether anybody has provided a separately written visitor that's none of the business of the compiler. And so if somebody went and just wrote a visitor that runs over IR nodes, potentially our extended IR nodes. So you just point it to an assembly, it goes and finds the assembly, looks at it, finds a visitor, instantiates that, and then runs that visitor. Now, as long as the visitor is a standard checking visitor, you can pass it in an error list and it can format messages appropriately for your language. And we can do this as part of the compilation step so that we can actually return and display these errors in the IDE instead of having to use a separate offline command line tool to do this. And when you're writing these checkers, it's already nice to do this using the CCI because it gives you essentially all the capability of reflection, but it also allows you to go into method bodies with a single object model. And it has these convenient standard visitors and standard checking visitors and a whole lot of plumbing that you can just reuse to do this kind of thing. This would be language specific because this is before we've done any normalization. So this kind of checker would need to know about all the AST-like nodes for this particular language. And that may be what you want. Okay, well, it's just... Or you could... what most people do is they want to be language independent and they want to just do the checking on IL. So we don't care where this came from. We'll write a checker that just takes a compiled, normalized IL and just checks it for various properties. So one could have a second extension point where after we've done normalization, we can now go and just invoke the standard checker, but still display the errors in the IDE. And moreover, at this point, we still have fairly complete source information in the tree. If you read in IL from disk after it's been persisted, a lot of the source information is gone. The PDB is not a complete record of the source information. So you could potentially give better error reporting if you do your checker at this stage. have line information and so on available. Where otherwise, you would just have a general message. Okay, so two. I think I'm going to get through the slide somehow. Another interesting thing is that if you have two different languages that have both been built with these common components, extending the same basic nodes, IR nodes, it becomes possible for them to cooperate because they have so much in common. So you can start, you can basically just parse these different languages and then graph together the trees. So you can envisage, say, that a source language can have here starts an embedded thing or script block or something in another language of this thing. And then you can go and the parser for the embedding language can arrange to find and invoke the compiler for this embedded thing. And that compiler returns back a tree, some IR tree, which the calling compiler can graft into its own tree. So you can end up with following a parse of some source with a tree that actually contains extended IR nodes from various different languages. Now this creates a new problem in dealing with this thing. So up to now, it was either a standard node or it was one of your nodes. And so you could fully take care of this in your extended visitor. But now you potentially can get to a node which is from some other language that when you wrote your compiler, you didn't even know it existed. So there is a way to do that. So it requires some help from unknown node types. So one of the things I didn't mention previous time we looked at this is there is this notion that a visitor, that more than one instance of a visitor for a particular phase can cooperate. So you can have several separate instantiations of looker that cooperatively provide the looking phase of a compilation. And so what happens is that when we get to a node that we don't know, is that we go and we get a visitor for it. And this get visitor method, by default, the standard implementation of that, has a probing scheme for saying, okay, well, I know I'm running the looker visitor. Let me go see whether I can find an appropriate visitor for this current node type. So it uses the type of the unknown node type and the name of the visitor, and it has some heuristic for finding a visitor for it. So if it finds one, it instantiates that visitor. It then transfers the state of the current visitor to that new visitor, so that the visitor for that other language has available all of the state that this visitor has accumulated. So this is how they get to cooperate. So every visitor is expected to have this method transfer state, which knows how to transfer its state to another visitor of its type. And so it transfers its state to that newly discovered visitor, calls that visitor, which now compiles its part, it's a little embedded thing, in the full context of what the other language has found so far. So it has all of the available information, scope chains and reference types and all of that stuff available. So it's completely in context of that at compile time. And then when it comes back, well, it may have modified that state, so we then go and transfers, we take its state and puts it back into the calling visitor. And since you can have any number of visitors calling each other, so you can have a whole chain of these things, there's that little recursive call there to run up the chain to update the states of all of these things.
So it's ultimately going to have to generate known AST nodes, though.
Ultimately, it all has to be normalized into IO.
Right, but at this stage of the game, we're not generating code, so we're limited to AST nodes that the normalizer knows about. Is that correct, Herman?
Well, when we get to a node that we don't know about, we find a visitor that does know about it. And it then does something with it.
Oh, so
and
when normalization.
Yeah, and the same thing happens with normalizer. So we find a normalizer that knows about it.
Do you have examples of real-world applications of this kind of cooperation?
ASP, any kind of scripting application, and if you think about it, that's what Blueprints was all about.
Right.
And blueprints had a problem that they were running into, well, how do we do statement completion and all of this IntelliSense stuff when we don't really have the context of the caller available? How do we tell the thing that compiles the blueprint about you will be compiled and running in this particular context? And I don't know that they've solved that problem, but it was a hard problem. Here it is essentially no problem because of all the way the componentization falls together. This becomes essentially a non-problem.
Well, you're still assuming, though, that they speak a common lingo that this transfer state to has succeeded in generating a state that the new language can grok.
Yes. So essentially you have to play by the rules. And so this only works between different languages that have been defined in the CCI and play by the rules. But if you do that, at that point it becomes a trivial problem. Of course, getting a language that plays by the rules is a big problem, but you can only basically shift complexity over the fence. You can never make it go away. It's just, where is it? It's always going to be somewhere. Now, the last thing I want to talk about is something that came out as a variation on this embedded language, is that you can, in a single source language, we have a way of taking an expression and marking it as being the property of a separate visitor. And we do this to do query compilation in X#. So it works on the basis of if you do a query on some variable, if the type of that variable has been annotated to saying, I know how to do queries, instead of the compiler trying to compile the query for this runtime entity, it will mark the region of the query as belonging to a visitor that's been identified by the type of the query object. And then when we go through the compilation, we do the same sort of scheme of calling out to this other visitor, and it decides how to do this. So you can have a single query syntax, but make it pluggable so that you, if the object that you're querying comes from an Oracle database, then you can have an Oracle query component which you can build in there. And you can basically make the query syntax work on data providers that you had no knowledge when you built the compiler. So the compiler becomes essentially pluggable, that you can add after the fact, after you've shipped, separate assemblies that modify the behavior of the compiler for the existing syntax of the compiler. So this is nicer than having embedded code blocks. There's a difference between having embedded SQL and having a single query syntax which just goes to whatever the appropriate SQL is, but you don't have to learn a new syntax every time. But it basically, it leverages all of this componentization. So this is a very broad overview of what we've been doing with the CCI, and that's basically all I've got to say. And we've just run out of time too.
I have a question about normalization and extensibility. As I understand it, you said that normalization takes into account these foreign nodes. I can write my own normalizer to normalize extended nodes from another language. Is that correct?
Yes.
So what I want to understand, and I'll give two examples here, is how this works when the extension of the language, when normalizations for the sub-language are no longer extendable to the super language. I'll give two examples. So in one case, let's say I have XSLT, and I've got a compiler, there's a standard compiler written for it, great, and I want to be able to add embedded script in my XSLT. So I basically have XSLT plus. So I compile this embedded script language to my own AST for it. However, it has a new rule now, which is that this script language may have side effects, may be non-deterministic. And XSLT previously didn't know about this, and previously the normalization rules for XSLT would have eliminated these script calls where possible and things like this that would not actually be valid for these script calls. To take a second example, if you viewed, say, the relational calculus as an extension of the predicate calculus, when you compile the predicate calculus, there's certain normalizations that go on that are only valid for expressions that are made up entirely of Boolean operators. As soon as any part of the expression contains a relational operator, that normalization is no longer valid. So how do you deal with that? The one normalization's already been written, right? The one normalizer, the super language.
Yeah. Okay. So these are tough questions. basically, if your language allows embedded code blocks as script blocks, and you get to one of these things during your normalization, you have to stop making assumptions. Is that unless you want to make it a prerequisite that no embedded language may have a side effect, you have to say that, well, when I call this thing, a side effect could happen.
I guess what I'm asking is, I would like to preserve many of the normalization rules of the original language, but my new language changes some of them. Not all of those normalization rules continue to apply to my extended language. And it seems like this extensibility doesn't really give me a way to pick and choose which of the normalization rules I'd like to keep and continue to apply.
Are you looking for a way to communicate between the different normalizers?
Possibly. I mean, as just one example with the predicate calculus and the relational calculus, maybe I would like a way to say, sure, you can apply your predicate normalization rules, but only if the expression is made up entirely of nodes from your language.
Okay, so
or to take the XSLT example, maybe I'd like to say almost all of the normalizations you perform are okay, but these 5 actually violate my extended language.
I don't think there's any particularly easy answer, but one of the things you could do is if you had a CCI implementation of this embedded language available, you could make a new implementation of that language based on the existing implementation and modify the thing to be more aware of who's calling it. So you wouldn't get this for free. You would have to do some work.
I was just wondering, because it must come up with X# already, right, where you're embedding, for example, X queries and X paths inside of C#, and the two languages have different concepts of normalization. I was just wondering if you'd already encountered this.
So the compiler plugin takes care of that for the most part, because all we really care about is when we get to a particular expression is, leave me a value on the stack. And we don't make assumptions about whether or not that expression changes the state or not. So the assumption you make in X# is fairly limited. You say, okay, well, here's a subtree as an expression. It can do anything. Right? This is imperative language, right?
So then you don't have a way to, for example, normalize some expression that combines elements of both languages. You can normalize each language separately, but the combined result doesn't really get normalized. Is that right? Yeah.
You're talking about extensions of the language that aren't blocked off then.
Yeah.
Unlike the ASP case where I said script block and then end block.
I kind of like, say, a for loop in C# and a for loop in XQuery to somehow have similar normalizations applied to both kind of seamlessly, but their rules are slightly different. And it seems like I can normalize one language as a blocked off component, like you just said, but I can't kind of cross that boundary between the two languages.
Well, we probably should talk about this offline, because I have a little bit of trouble understanding exactly what the problem is. Probably it's not easy, but I expect that this way is going to be as feasible as any other way that you can.
Yeah, I was just wondering if you had addressed this yet already.
Not specifically.
The location for the source code or demo.
So there is no nicely packaged up, redistributable source code. You can enlist in a source depot and get hold of the stuff. So, yeah, I forgot to mention at the beginning, X# is still confidential and shouldn't be discussed outside of Microsoft. CCI itself can be discussed. And will be distributed separately from X#. And the intention is that it will be distributed in source form as well. Yes.
In the CCI sources, do you have a sample simple project that can be used as a base, a kind of quick up and running basis?
Yes. So there's two languages that are based on a CCI, X#, and there's a little language, much smaller language, HScript. And these have projects. Their implementation of the project is essentially trivial. It just sets registry entries and then relies on the base implementation to do all of the other stuff. So there's not much example there in terms of how to customize these things. That will probably be forthcoming in the future, but right now there's not much. And much of the project code still has to come.
Yeah, I'm not so interested in the project fragment as just if somebody were trying to start up with this and implementing a simple language, what would be the best place to start? And it sounds
Yes.
like the HScript or something.
HScript is probably it's a very simple language, so just looking at how that's done is lacking any documentation, which of course there's no documentation, is going to be the simplest way to try and figure out how to do all this.
Herman, and as a strategy, does it make sense to start with the language service, do the scanner and parser, and then you can kind of get something basic up and running in VS and then move on to the compilation phases?
Yeah, you could do it that way, yes. So the first thing you have to do really is write the scanner. Right. And following that, you write a parser, and then you already have some part going.
Right, at that point, you can run the language service.
Yeah. But basically, since all the standard IR node types have all this functionality there already, and if you look at something like HScript, all of that plumbing is there, all of the extensions are there already. You would just basically start with your language, which is a zero extension of the basic functionality, and then add the extensions one by one.
You can productize this.
In the long run, I think it makes sense for the binaries, the system compiler framework, to become part of the .NET runtime redistributable. In the short term, it will be a download available from somewhere. We haven't worked out the details of how to do that. If you need to redistribute the things in the short term before we've made it generally available, then we can come to some private arrangement. So I believe ASML has already redistributed early versions of the binaries. And FXCOP will be doing that as well. So it's possible. Thank you.